In the modern era of artificial intelligence, AI subfields can be categorized into four main application fields, starting with computer vision, which is the machine's ability to understand visual context, either images or videos. Then we have natural language processing, which is concerned with the interaction between computers and human natural language. Speech recognition then, concerned with translating human natural language into text. And finally, robotics, which is a subfield of design and development for robots that can assist in some of the tasks carried by humans. Robotics can be seen as the interface between artificial intelligence, electrical and mechanical engineering, and control as well. Robotics shows to be very important in manufacturing, especially in automating risky tasks. On the level of technology enablers and algorithms, we have machine learning and deep learning. Deep learning is a subfield of machine learning. Both of them are behind the current revolution in artificial intelligence, as they serve other application subfields, achieving accuracies we never achieved before. We will cover each of these subfields in detail in the next slides. Machine learning is the subfield of artificial intelligence that is behind the current revolution in the AI applications. It's a subset of algorithms that makes the computers learn the required task by feeding them with data, without the need to be explicitly programmed. These algorithms are basically statistical algorithms. As a high-level explanation, data scientists always have an objective mass function to these algorithms, along with the training data. And the algorithm learns by reducing the cumulative error over all training sample. Systems based on machine learning algorithms improves performance in a given task with more and more data. The more various input data, the more the system is able to generalize to unseen data. Learning is different from traditional programming. In traditional programming, you need to specify to the program what to do for all conditions explicitly, and the code needs to cover all possible scenarios and the required actions for each of them. Usually, traditional programming exhibits a lot of if-then rules, and the code can reach thousands of lines to cover all the possibilities. On the other hand, in machine learning, you let the computer to discover the hidden insights from the data without the need to define any conditions. All you need to define is the model that best fits the problem you are trying to solve, and it will learn during the training process all the characteristics behind each class or category. Okay, now we know what is machine learning and how it's different from traditional programming. Let's talk about the different approaches of machine learning and the tasks each of them solve and the different algorithms they have. The two major approaches of machine learning that are most widely used are called supervised learning and unsupervised learning. Supervised learning means the data should have a correct result or label, so the machines learn them too. Unsupervised learning means there is no labels or correct answer. The cost of labeling the data usually is very high because you need to have humans to manually label large amount of data. That's why unsupervised learning solves a wide range of applications. And also, semi-supervised learning now comes in between as an intermediate approach between the supervised learning and unsupervised learning, where you have a small amount of labeled data along with large amount of unlabeled data. And finally, we have reinforcement learning, which is totally a different approach and considered to be a new approach in machine learning. In reinforcement learning, there is an agent in the environment that learns by maximizing the reward points and decreasing the punishment. One of the tasks that comes under the supervised learning categories is the regression problems. Regression means estimating the relation between the outcome variable and the input or the independent variables. Regression problems can be single variant or multivariant regression. Some examples on this include predicting the demand for a specific product for the next month depending on the current sales and other factors, or predicting weather conditions, or also predicting house prices based on the area, the location, the services, and so on. Another important task in supervised learning is classification, where the model will classify the input data into predefined specific classes or categories. And of course, the model was trained on various input data that will make it able to define the different characteristics of each class or category. Classification can be either binary classification or multi-class classification. Classification applications are being widely used now in computer vision and natural language processing areas. Some examples include classifying feedback into positive, negative, or neutral, classifying transactions into fraudulent or not, classifying emails into spam or not, and so on. In the unsupervised learning area, clustering is the most widely used, which is organizing the data into different clusters or groups based on their characteristics. For example, segmentation of different customers. Association rules also part of unsupervised learning to discover the relations between different variables in large data sets. An example of this is basket analysis techniques to understand customer purchasing patterns. Also, dimensionality reduction techniques are part of the unsupervised learning area. Is a subfield of machine learning that builds multi-layered network that simulates the human nerve system. So simply we can say that machine learning is a shallow network, while in deep learning we stack multi-layers into one network. Both of them have trainable parameters and learn by trial and error. The main building block of the deep learning is neural networks. Neural networks are computing systems inspired by the biological neural networks, consists of series of layers of neurons connected to each other. Each neuron combines many input and produces one output through the mathematical function. There are three main types of neural networks, and we will discuss them in the next slides. Starting with the feed-forward neural network, which is the simplest neural network. In this kind of networks, the information moves only in one direction, which is the forward one, from the input layer to the output layer. The output of each neuron of the hidden layers works as the input to the next layer. The training process done on the weights assigned to each neuron known as the matrix W, and also we have the Bayes matrix called B. Then we have convolutional neural networks, or CNN for short, which are commonly applied to analyzing visual context. CNN applies convolutional process on the input data through filters, and the result is passed to the next layer. The training process here is done on the weights of the filters. CNN usually use relatively little pre-processing techniques compared to the other image classification algorithms. This means that the network learns the filters that in traditional algorithms we hand engineer them. We can pass images directly to the CNN without pre-processing, and it will learn to extract the features itself. Finally, CNN are most commonly used in combination with feed-forward neural networks to serve the computer vision applications. Neural network type is the recurrent neural networks. What makes recurrent neural networks different is that they remembered the past, and their decisions are influenced by what they have learned from prior input while generating output. RNN works perfectly for long dependencies and variable length inputs and outputs. That's why they best fit for the text data. One of the most widely used RNNs is the LSTM architecture, which stands for long short-term memory. So, important question in this area, what is the added value of deep learning and how it's different from machine learning? Machine learning requires a lot of feature engineering to extract the features from the data and find correlation, while deep learning don't require this. You just input the data into the network and it will learn the embedded features behind the data points. That's why machine learning, deep learning best fit for unstructured data like images or text, but also deep learning require very long training time with respect to machine learning. Then, why do we still need machine learning? because deep learning networks are very deep networks that require training of millions of trainable parameters. This also requires hundreds of thousands of data points, which is not always available. And of course, this requires huge computational power. And also, some researchers still show that machine learning works better for structured data. Computer vision is concerned with the techniques and algorithms used with images and videos to develop solutions that can understand the visual context and act accordingly. An advantage of computer vision systems with respect to the human visual system that they can support different image modalities besides the visual spectrum. Algorithms can perform object recognition in the infrared bands or in modalities like radar-based imaging. One of the main applications in computer vision areas is object detection. Object detection is about localizing and classifying all different objects in an image. We can see here an example of object detection that identify and classify different objects, including cars, traffic lights, bikes, trees, and so on. Object detection comes at the core of many other applications like face detection, pedestrian detection, weapon detection, and also it can serve many other complete use cases as well. It's very well known that deep learning performs far much better than traditional approaches in computer vision. The development of convolutional neural networks, increase in computational power, as well as increase of the amount of data available for training neural networks has had a tremendous influence in the field of computer vision in the recent years and are responsible for a big jump in the ability to recognize. Machine learning and deep learning introduces an end-to-end learning approach where the machine is given data sets of images annotated with the object classes. The deep learning model is trained on the given data set. The neural network discovers the underlying patterns in the classes of images, and in deployment, we just pass the input data to the neural network to identify the classified object. Machine learning and deep learning are the enabler of the current wave of solutions in computer vision. Research institutes and companies invested a lot in the data as well, which is the important part for the application development with deep learning. Here we can see on the top ImageNet dataset, which has 14 million images organized according to the WordNet hierarchy, and almost each class has around 22,000 images. Giant companies in AI area competed every year to win the challenge for ImageNet and build state-of-the-art architecture to achieve the best accuracy in image classification. On the bottom, we can see COCO dataset, which stands for Common Objects in Context. It's used in object detection, segmentation, and captioning a problem. Dataset contains 91 common object categories, with 82 of them having more than 5,000 labeled images, and many other datasets that can support various applications in the computer vision area are being developed. Computer vision research helped to support almost all industrial sectors, especially with the availability of cameras everywhere, providing tons of footage. Here are some examples of the computer vision applications that are the core behind many industrial use cases. Some of them are used alone, and some of them are combined to achieve further functionality. Many of them are grouped together to form complete use cases. Starting with image classification that classifies the whole image into a single class. Then we have object detection that we already explained. Also, face recognition. We can say that face recognition is most widely used in computer vision area. Applications of face recognition range from attendance systems, prohibition of watch list, border control, public safety, and many others. Image segmentation as well, to classify each pixel into one class and group all the instances of the same class. This application is important in scene understanding use cases like content-based image retrieval, medical imaging, traffic control systems. Also, image captioning to generate textual description of an image. This helps in virtual assistance and text-based image retrieval. Also, human pose estimation, which is the localization of human joints like key points, elbows, and wrists. The application of pose estimation include activity recognition, motion capture and augmented reality, training robots, motion tracking. Also, emotion evaluation to measure customer satisfaction levels, gender and age detection for segmentation and marketing activities. All of these applications can work together to get further insights and increase the productivities, and many of them are using in almost all industrial sectors now. We can understand how machines can see the way we see, but what about our reading and our hearing senses? Can machines really understand the way we talk or the way we read? This is I think is very important question here. This sentence, for example, say, "Hello, artificial intelligence world." Everyone here can simply understand it in English and most probably in one or more other language. Let's discuss how more machines can understand this. Machines understand the human natural language is part from natural language processing. Natural language processing is about the techniques computers use to process and analyze large amount of natural language data, and understanding the context of the data, extract the required information, and provide the right response accordingly. Natural language processing pipeline starts with the plain input text, then data pre-processing tasks to split the input data into separate tokens, remove stop words, reduce words to their root or base considering the context. Then data representation, representing input tokens into numerical format. Then the machine learning algorithm or deep learning architecture, and this differs based on the problem we are solving. Then the output layer. The output can be a class or can be a generated text as well, based on the problem we are solving. The level of the natural language processing tasks, I will start with sentiment analysis to help analyze reviews and feedbacks, and this can be very helpful in customer service and retention programs, products evaluation, and marketing activities. Also, we have topic modeling to highlight abstract topics within the text, to discover hidden semantics behind the text. Also, this can be used in document summarization, which is very helpful in the research field, and also it can be used in recommendation engines. Text classification is another important task to classify the documents into specific predefined topics, which is widely used in spam filtering, mails routing, news classifications, and many others. Still, we have named entity extraction to extract public figures, names, addresses, also question answering, autocorrection, spell checking, and these tasks are important in chatbots and virtual assistants. We have also automatic machine translation. All of these applications either are used directly or combined together for further functionality. To process the natural data, huge research is being done to find the right representation for the text data, and also to develop the right neural network that best fits the nature of the text data that introduce lots of dependencies. On the level of text representation, we used to use word embeddings to represent the words with numerical vectors. These embeddings are context independent. These models output just one vector for each word, combining all the different senses of the word into one vector. Most common word embeddings include glove, word2vec, and fast text. Now, the new trend is to use the contextualized word embeddings using complete pre-trained language models. So they generate different word embeddings for a word that captures the context of the word. That is its position in a sentence, like BERT model and GPT model. Talk about speech recognition. There is always a misperception that speech recognition is part of natural language processing. Speech recognition is concerned with translating human voice into text. also known as speech-to-text or automatic speech recognition. Speech recognition usually incorporates signal analysis, feature extraction, acoustic models to detect the phonemes, convert them into words. Some NLP models are used at the end of this process to solve the context issues like language models and accent models. Here we can see a complete automatic speech recognition pipeline. The main three components of an ASR pipeline include: first, the feature extractor, audio signal pre-processing using normalization and windowing, and the output is the spectrogram. Second, the acoustic model, networks that predicts the probability distribution over vocabulary characteristics per time step. And third, the decoding. In this step, either we choose the characters with the highest probability without regard to any semantic meaning and then remove the repeated characters, or use a language model to add context and therefore correct mistakes of the acoustic model. And for clarity, language model is a probability distribution over sequence of words, so you can predict next words based on the surroundings. Finally, let's see how speech recognition and NLP work together in conversational AI systems or virtual assistants. There are three main steps in any conversational AI system. First, automatic speech recognition, to process through audio signal and get the transcript text from it. Second, the natural language processing is used to derive meaning from the transcribed text. And last, the speech synthesis, or the text-to-speech, for artificial production of human speech from text. In the virtual assistants, also, automatic speech recognition is used with natural language processing, and the output can vary from speech generation to implementing specific tasks like doing research, calling a number, retrieving any kind of information. And the applications for virtual assistants and conversational AI systems range from finance, e-commerce, healthcare, and many others. Before building the machine learning algorithm, first we need to understand the business problem we are solving, then identify the required data to achieve the objective goals. Then comes data collection or generation if the data is not available. Once the data is ready, here starts the machine learning workflow. Data pre-processing comes then, including data cleaning, outliers handling, missing data handling, removing duplicates. Then comes data preparation and feature extraction, including features reduction, putting features in categorical values, and get the data ready for the models. Then model building, choosing the right machine learning algorithm or deep learning architecture for the problem, tune the hyperparameter, and then training the model and evaluating the model. Once this process is done, we test the model on unseen data to see how the model will generalize. If the model doesn't provide the required accuracy, we do fine-tuning, change some parameters of the model, and do the retraining again till we reach the required accuracy. Finally, we come to the model deployment and inference. Most popular frameworks included in this workflow like TensorFlow, PyTorch, Keras for building the deep learning models, sklearn for machine learning algorithms, Pandas, Matplotlib, Seaborn for data preparation and visualization. To be able to achieve state-of-the-art performance in the various applications, we need to train very deep neural networks on millions of data elements. The network complexity is exploding. Starting from 2015, it became possible to train very large models on millions of data elements. In 2015, Microsoft ResNet architecture, for example, was around 60 million parameters with 7 exaflops. In 2016, speech recognition, deep speech, reached around 300 million parameters. And in 2017, things changed with Google Machine Translation. We started to have billion parameters in neural network, resulting in required computational power of 100 exaflops. Do the calculations, 100 exaflops can take 2 years in dual CPU server. Here came the GPUs to the rescue. GPU computing played a game changer in the development of AI solutions. GPU computing is parallel computing with multiple processor architecture. GPUs accelerate the parallel regions by spreading the computation over thousands of cores. Today's CPUs have 6, 8, or even 12 cores, while GPUs have thousands of cores in a single chip. That's why it can process and render high-resolution images and videos and do other matrix processes. That's why GPUs best fit for deep learning training, which incorporates a lot of matrix processes. Also, many GPUs are combined with multiple CPUs to achieve higher performance together. This algorithm is used to classify different flowers. First, the best CPU can achieve maximum 5 images per second. If we use 1 Volta V100 GPUs, it can achieve 900 images per second. And if we use 8 Volta V100 GPUs, they can achieve 7,000 images per second. We are even going much bigger. If we have a look on natural language processing, for example, now we have pre-trained models that can be generalized to multiple natural language processing tasks. Started with BERT architecture and GPT architecture. Huge developments is being done on the models. We can see on the left the complexity with respect to training parameters. The latest in this area, for example, is GPT-3. GPT-3 has 175 billion parameters. Can we imagine the numbers? If we train GPT-3 on a single V100 GPU, it will need 355 years to finish the training. On the level of the datasets also are exploding, and availability of data is increasing, either in computer vision area where connected cameras created huge availability of data, or in natural language processing where digitization also increases data availability, either structured or non-structured. And of course, lots of companies invest a lot in datasets creation. In natural language processing also, for example, we now have many corpuses that has millions of words. With English Wikipedia dataset, for example, that has 2.5 billion words, and many others, ending with the largest open source large crowd that has 800 billion words. With this explosion, either in the data or the network models, we need more of DGX systems to work together to handle such complexity. So last thing to mention in this area that it's not only about the machine learning part of the solution. Actually, the machine learning code is very small fraction of the overall system. Data management and maintenance, analysis and visualization tools are also very important. There are also lots of other factors to consider on the level of the hardware infrastructure to assure reliability and high availability. Configuration of different components, process and resources management is also very painful. But DGX systems also helps a lot in this area through providing a complete stack with all the required support on all levels and all the resource management software needed. That makes things easier for both data scientists and DevOps engineers. Framework is a framework that provides functions and libraries to help data scientists build and train their AI models. Without these frameworks, each data scientist will need to write everything from scratch, which costs a lot of time, effort, and money, as well as this doesn't guarantee the quality of the code and compliance with best practices. That's why every AI vendor and data scientist are using the AI frameworks, and these frameworks are prerequisites, and you will be always asked to install them by your customer. There are lots of frameworks, and most of them are open source, but they are backed by technology giant companies. The most popular framework that most of your customers will ask about or will know it is TensorFlow, which is backed by Google, and also PyTorch by Facebook. When a new version of the framework comes out, Nvidia takes its code and optimizes it to Nvidia GPUs and makes the optimized version available to use for public. Optimization of the framework is also done whenever a new CUDA version is released or a new GPU comes out. Hence, there are monthly releases of the optimized frameworks. The optimized versions from Nvidia are at least 2 times faster than the community version, so always download the optimized one for your customer. As we mentioned, these frameworks are available for free to download from the NGC, which we explained before. All that you need to do is to log into your NGC account, search for the required framework, and follow the couple of comments to download them on the system. But before that, you need to check for a couple of things, as you will see in the next lab. But overall, it's a simple process like downloading any other software.
So now we will see how to install the required deep learning framework or OI framework and see how to deploy or run a simple AI use case on the system. So now we are on the system, and this is the terminal, and say for example the customer wants you to install a deep learning framework, for example TensorFlow. So before you install it, you need to check for multiple things first. You need, for example, to check if the GPU driver is correctly installed or not, and then you need to check if Docker is installed or not. On the DGX, all of these are already installed for you, but just you want to check for that. So the first thing is to check for the GPU driver, and the command to do that is Nvidia -SMI. Now, if the GPU is not, the driver of the GPU is not correctly installed, this command will give you an error. But if it's correctly installed, it will display you information about the GPU. So if we hit enter now, it correctly displays. The information here is split into 2 sections. The first one here is related to the GPU itself, and it contains, for example, the GPU number, which is 0, meaning that there is only one GPU with an ID 0. Then the GPU name is GeForce here, and the GPU memory utilization, everything regarding the GPU. It also displays you the driver version and the CUDA version that are currently installed. The next section is regarding the processes that are running and utilizing the GPU. So here you have multiple processes, the type of each one, whether it's running on GPU or CPU, and the memory utilization of each process of the GPU memory. Okay, this was the first thing. Now the second thing to check for is Docker, and this is a platform for containers as explained. So the command to do that is sudo docker --version, and sudo here means super user, and you need to use it to check to use Docker in general. So when you press enter, it should check the version and print it for you. Okay, so now it's installed, and this is the version. Okay, now as explained, you want to install the deep learning frameworks such as TensorFlow, and as has been shown in the slides, all what you'll need, you will find it on NGC from Nvidia, which is Nvidia GPU Cloud. So first we go to Nvidia GPU Cloud, just search for it, and now you open it. So you select containers, and you write the name of the containers that you're looking for. For example, you are searching for TensorFlow, so you search for it, you find it here. When you click on it, it opens the description, and here is the bool command. Now the bool means just to get to download the image of that framework. So you just copy that command here and paste it in your terminal. And don't forget to add the super user first. Okay, now what this command will do is that it will get the TensorFlow image and download it to your computer. Now we press enter. And now it's starting to download. It will take some time, so I will pause the recording here, and we'll have some questions, if any, until it downloads.
Important concepts and terminologies that will often be used during your conversation with your customers, so you need to understand what is behind them. When developing an AI application, the process is split into two main parts. The first part is called model training, and the second is called inference. Model training is the process of building the AI model and feeding the data to the model to learn the required functionality. This is the part which is usually computationally intensive and takes months to finish. The reason behind this is the data usually is very big, very big, in gigabytes and sometimes petabytes, and the calculations that needs to be done on them are very complex and needs to be done multiple times, not only once. The computations could be in exaflops, which is billion mathematical operations. Now, after the AI model has learned or trained to do what's required to do, it's time to be used in production, to be available for users to use, and the process of making it available for using is called inference. Inference is not that computationally intensive as much as training. Still, a lot of computations need to be done to provide the users with the results. Some AI applications require to provide the results instantly, like Google Translate, for example. It will give you the translation just as you finish your sentence. Or Alexa or Siri, that needs to understand your sentence and act accordingly. Or autonomous cars that need to stop immediately if they see a person on the street. To make the applications to be able to do this real-time inferencing, data scientists always use two main ways. The first is to run the applications on GPUs to do the calculations more fast. And the second is to optimize the AI models themselves to reduce the needed calculations and modify the software to act faster. And here comes additional frameworks that you might be asked to install as well. The most popular one is TensorRT from Nvidia, which again can be found and downloaded directly from the NGC. Next, we will show a lab on how you can run TensorFlow framework that we downloaded previously. We will show a quick example to train a simple clothing recognition model.
Okay, so now TensorFlow image is already downloaded in the system, and let's verify that. So we have two ways to verify that. The first one is to try to pull the image again, and in that case Docker will check if the image is already on the system, and if it's there it will tell us that it's already downloaded, and if not it will pull it again. So I will go there again, copy the pull command and paste it into the terminal. Again I'll write sudo, press enter. Asks me for the admin user. Yeah, the status is here, image is up to date. Okay, the second way to check for that if it's downloaded or not is to just list all the images that we have on the system. Yeah, I forgot to write sudo, that's why it was showing the error here or the warning here. And now it lists all the images that I have, and you search between them on the image that you want to check, and it's here, TensorFlow, and this tag or version, which is the one that we want to download, the latest one basically. Okay, now how to run TensorFlow for the developers to start developing. So if you go back to the page of the TensorFlow image on NGC and you scroll down, you have an explanation of what is TensorFlow and how you run it. So here's the procedures and here are the commands. So if you have the Docker version, which is this version, and actually we checked it and we know that we have this version, then this is a command to run, and I'll explain briefly what this command means. So docker run is actually the command you tell Docker to run an image. Okay, then the parameters that follows is dash GPUs, and here you specify that you will be running that image or container on GPUs as well as CPUs, not CPUs only. After GPUs, you specify which GPU to run that container on, and if you have multiple GPUs you can run it on all of it. So for example, you want to have an application that runs all the 8 GPUs that you have in the DGX, or you want to run only on one GPU, so you specify the GPU ID here, 0, 1 up to 7, or all of them. Then dash IT, which means interactive, so when the container is launched you get into that container and see what's happening there. And now dash RM, which is remove, and it means that the container should be removed when we finish the work. Then is dash V, and this is an important one. That means that there is a specific folder that contains, for example, my codes and my data, and I want that folder to exist in the container. So TensorFlow has access to that folder or to this data to train on. So you specify that dash volume or dash V, which means volume, and after that you specify the path of that folder or volume that you want to mount inside the container. So you first specify the path locally, and then you specify the path that you want to be mounted inside the container. You put the local directory, then the container directory, and lastly you specify the image name that you want to run. So you will take that command. I will just clear the screen and put the command here, and now I will adjust these parameters according to my data. So for example, I keep everything as is. The local directory, I will specify the directory here, so I have put my codes and my data in the home directory slash IngramAI slash DGX models slash fashion. And this is a file that I want to put or mount there in the container. Then I just specify the path inside the container which the files or the folder should exist. So I wanted to add it inside the container in home slash codes. Everything will be there. Then I specify the image, and you should notice here that the tag or the version is not specified. It's actually a generic format. So I want to specify the version here instead of these X's. So I go back and I check which version did we download. It's the 20.11-TensorFlow 2. So I write that here, 20.11-2 TensorFlow 2, and of course I will put the pseudo word. Yeah, that's it. Let's run that. Now it takes some time, but because there are multiple things running on that system now. For the systems that you will be installing and running this framework on, it will be on the fly. It will not take that much time, unless there is a lot of data that needs to be mounted inside the container. Now, as you see, because we have chosen an interactive mode when we run the command, we are now inside the container itself. So if you remember, or as you can see here, I mounted my code into home/codes. So if I change my directory to home within the container /codes, okay, let's go home, and I want to list, yeah, codes. Actually, it names the file as codes. Yeah, this is the code here, and inside that code, data scientists import the libraries that they want. So actually, TensorFlow is imported as a module, or as a framework is imported inside that code, and you run that code within the TensorFlow container, so it can use it. If you want just to run it, the code is a Python code, so you say Python and you run the file. Now I want to show you what this code actually is. I will open another terminal here so I can show you what is this code. I will go to Jupyter Notebook. Okay, now we have the code here. This is called a notebook that data scientists often write the codes in and experiment with their data. So as I said, the TensorFlow framework is imported in the Python code in this notebook to use it for the training and the modeling of your network. You don't need to bother yourself with that. You just to understand what is it and how everything works. This code is actually running an image classification model. So this code develops a network that should train on images, and actually it's the output is shown here. It trains on images to classify them. So the data that we use are actually called image data, and it's data for clothes, and you want here the system to automatically detect or know or classify the image that it sees. So it tells that this is a t-shirt, this is an ankle boot, for example, this is a pullover. So you want it to identify which product when seen by the camera. And here if you scroll down, you identify the model, and here is the training output. So we trained on 15 epochs or 15 iteration over the data, and this is the accuracy that we reached. The last one had 92% accuracy. So now if you have this model and you give it a new image of a pullover, for example, it will automatically detect it. And this use case, you might see it simple, but it's used a lot, and it has many commercial use cases. I'm sure that you will be presented to that in the slides. Thanks, and if you have any questions, please ask. Thank you.